of these.
Yeah, it is, but it's a little bit weird. Okay, so the question we're dealing with, and this is another kind of nasty problem, and I'm realizing that I I'm not sure to what extent I went over the difference between K and R, but that a K value and an R value, and that's really what this comes down to. So let's just back up a little bit and look at what K is. So K. So again, this is quiz 2 problem. Problem 6. And what we're looking at, so K is heat. I find that I'm always writing the next letter. Like somehow my hand is ahead of my brain. Do you guys do that ever?
Yeah.
So I was trying to write the word heat, loss, and I wrote H-E, I wrote heel. I put the L instead of the, I don't know what either something has to speed up or something has to slow down.
I just skip letters. Like for R, sometimes I just write E. Like I just end it. I don't do the AR.
Yeah. So here's where some dimensional analysis comes into play. So K is heat loss coefficient. And it's and the dimensions. Again, I'm going to put these brackets around this guy. Equals watts per meter squared Kelvin. Now, another thing I want to get on here is R versus U. And let's look at the, I hope it's in this book somewhere. Let's just look up thermal conductance.
Is that like the R value? And
yeah, that's exactly R value.
so the U is just the inverse of the R value,
That's exactly right. Thermal conductivity 4D8. Let's see what he's got for R value. I'd like to just stick to the book and not go out to the internet on here. Doesn't really have R value. 223. Let's look at 223 here too. I'm just looking in the index here for thermal conductivity, page 223. Yeah, okay. R versus U, and you're exactly right. R equals 1 over U, or U equals 1 over R. Now, let's look at the, so U is thermal conductivity. And if we look at the units of U, so again, the brackets just mean we're looking at the units. And let's see here. Yeah, that's good. We're looking at the units. So you could also use the brackets to mean dimensions, but I don't want to make up a new set of brackets. This is watts per meter Kelvin. So here's the question: which of these two? So they look a lot alike. K and U look a lot alike, and the question, and I'm sorry too that the K's are looking a lot alike too. I don't. Yeah, let me. Yeah, the coefficient is lowercase. Let's make the big K look more like a big K. I'll put some serifs on it. So that's K for capital King Lord Kelvin himself right there. And then the little k is the heat loss coefficient. Now, which of these is a intrinsic property and which is an extrinsic property is the question. So what we want to go back to is our electrical analogy. Which one of these is resistance and which one is resistivity?
Resistivity is the U, right?
It'll be resistance.
It's a little bit backwards, but yeah, so this R, this thermal resistance, is similar to resistance. I'm just going to write electrical resistance. And so essentially, I'll just kind of write it down here, 1 over K, because K is a lot more like U than R is, because U and R are opposites. 1 over K is similar to electrical resistivity.
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 Resistance.
Yeah, so R is similar to electrical resistance, and 1 over K is similar to electrical resistivity. So for example, copper has a resistivity, but a long number 12 copper wire has a greater resistance than a short number 12 copper wire. So that's the difference. So K is a material property. It's intrinsic to the material, and these two guys down here are extrinsic. It depends on how much you have,
Yeah.
because the resistance depends on how long the wire is. Okay, so hopefully we understand the difference between K and R now. So, and you could go and look in a book to see what the K value is for different materials. But then, when you go to the hardware store and you buy insulation, you're going to buy, and so let me just draw it this way. Just draw a couple of sheets like this. There's one sheet. There's another sheet. And this is just, I'm just going to call this, let's just call it blue board. Everyone's seen blue board before. And here's blue board number 1. And here's blue board number 2. And this guy right here is thickness 1. And this guy right here is thickness 2. And let's just say, for the sake of argument, that thickness 2 equals 3 times thickness 1. It's 3 times thicker. You just go and measure it. But here's the kicker, is that it's blue board, so K1 equals K2. The blue board itself has the same thermal conductivity, because it's blue board. But R2 equals 3 times R1, because it's 3 times thicker. So that's the difference between the thermal conductivity coefficient, K, and the R value, the thermal resistance. Okay, so now let's get back. And that should be, I think that should be super clear now. So now let's go back and look at the first time that K is mentioned. It says that, and I'm just reading right down here in the middle of page 26, it says the thermal losses are dependent on the temperature difference between the absorber and the air. So what we're looking at is, I'm just going to call this let's do it this way. He uses theta for temperature, and I'll use big A for absorber, and I'll use temperature out here, little a for air, whatever. And delta t, or delta theta, equals the difference. It equals theta big A minus theta little a. And what he's written is that Q dot L equals K delta theta, right? Because you'd read this question. Let's just go back to the question. It says, you have designed a solar thermal system. Notice all he's making your house. After some measurements, you determine the temperature of 20 C. Saw that right there in the book. You're losing about 50 watts from the system. We know that Q is measured in watts, and you have an effective area of 4 square meters. So this is the equation of the book. Now, let's go back and see if the equation is written correctly. Because we know that Q is written in watts per square meter. And we know that, or no, hang on one second, sorry.
K is watts per square meter Kelvin.
Yeah,
The
and
temperature is Kelvin.
yeah,
So those cancel each other out, right?
yeah, equals equals and then yeah, so that's watts per square meter Kelvin, and then this guy is just Kelvin. So it's nice. Everything cancels out, right? The Kelvins go away, square meters go away, watts go away. Now, so like, gosh, what the heck did I do? What's missing from this thing? Well, I told you that the effective area is 4 square meters, and you can see it in this equation. There's no place for the area. So what you have to do, and what we're going to do right now, is get a little creative and realize that the way the authors have described it, the Q's in this case are it's power per area. So if we rewrite this, and I'm just going to write, I'm going to rewrite it like this, Q dot, and I'm going to write losses total, because right now we just have per area equals, and I'm going to make this up, but I'm going to show you why I'm making it up. K A delta theta. Now, where the heck did the A come from, and how can I justify that? Well, the total losses is just watts. It's not watts per area, it's just watts. So now we've got watts here equals, and now we've got, again, K is watts per square meter per Kelvin. We didn't change anything there. Area, of course, is meters squared, and then K is in Kelvin. Let me make the big Kelvins there. Make those K for Kelvin big, and then we'll leave the little ones little. Okay, so now the units work out. We've got watts, meter squared, Kelvin, Kelvin. Good. So what you do now is you take this guy, your total heat loss, and let me just pop it right on down here, and we can now solve. We'll solve for K, because what the question asks for says, what is the heat loss coefficient for your system? And so we can just rearrange and like so, and just say that K, again, little k, equals Q dot and again, the L stands for losses, and the T stands for total. So it's not on a per unit basis anymore, because that's what I gave you. And now we just have A over delta T. And from there, I told you that you were losing 50 watts. So here's your 50. And I told you the area was 4 square meters. And you know your delta T is 20. So from there you've got basically 5/8 equals 0.65. 0.65, 0.625, and the units there have to be, I'm going to try to jam this in there, watts per meter squared Kelvin. And you might look at that and say, well, gosh, is that a lot? I don't know. It's 625 milliwatts per square meter, and per Kelvin. And I don't know if you guys have covered this or if you've taken the geothermal, but the Earth's average radiation constant is about 60 milliwatts per square meter. And then, you know, if you divide that by the average temperature of the Earth, and gosh, I don't know. I guess what I'm saying, it's kind of in the right ballpark as to what the Earth itself is radiating. You know, it's on the right order of magnitude anyway. So you might look at that. You know, if you knew the radiation constant of the Earth, you'd look at that and say, okay, that's about right. It's in the order of milliwatts per square meter. Okay, does that explain what K is? And I apologize, I didn't really cover that well enough in class, especially to dig into this level. So I can give you some redemption on this for the final, but hopefully you understand the difference. And so I think that some question like this is pretty fair game. If I were to go, you know, say what R versus K, I think that's pretty fair game. Intrinsic versus extrinsic, I think, would be pretty fair game for the final. I think we kind of understand how tricky this little chunk of the book can be, but the way I've seen this book, there's the first few pages are pretty heavy on the theory, and the rest of them are, gosh, I don't know. I don't want to say boring, but the rest of the stuff, you know, I'm just looking forward to like page 843, calculation of fan power. That stuff you're going to get in Troy Savage's class anyway. I'm looking forward to domestic building, Potsdam, Germany, in Section 8. That's stuff that you're going to get to in Building Energy 235 anyway. So that's why I'm like hitting this first chapter so hard. The other thing, I don't know, I guess I look at these things like Chapter 4, where starting up, maintenance, and servicing, a lot of that seems like kind of common sense to me. It kind of seems like,
Yeah,
I mean, you're,
on and on about this valve and that valve, use this valve.
you know, and meanwhile, Joe's over here like, just put some grain alcohol in and call it good. A lot of it's kind of common sense. This stuff we're going over now, not common sense.
Right.
This this is very hard-won scientific engineering theory that, I mean, you can make a career as a building technologist and probably not know this. But on the other hand, if you're like making a career as a building technologist, and all of a sudden you're like, holy crap, man, why are we doing it this? You know, it might occur to you that there might be a more efficient way to do something, you know, based on your knowledge of thermodynamics, and that's hopefully the value that I'm giving you here. Okay, let's take another little break, and then we'll finish up the quiz. So I think I'm killing two birds with one stone here. I wanted to give you an idea of what was going to be on the final, and I also wanted to grade this quiz at long last. And so I think I'm doing both at the same time, so hopefully this is helpful. I just want to say, hey, Will Stallman, thanks for listening. I know you are. Yes, my office is still really messy, but whatever. We're going to clean it up right when we're done here.